Hi, we're Group KKED.
I'm Daniel.
I'm Kurtz.
I'm Evelyn. I'm Kenny.
And today we're going to be performing experiment 4, which has to do with percent error and difference. Let's get into it.
For this experiment, we use the same materials we use for lab number 3. We're going to be using the air fluid and this. First we turn it off, and then the air comes out of this little hole and starts moving the glider. First we put the glider. We put it right here, and then right here it has the mesh. We're using 2 grams and 5 grams, so it equals to 5. To 7, sorry. To make sure we have 7 grams right here. Put it on the balance. And then remove it to make sure it's balanced. And then we have the sensors. The sensor will project it, the glider moving to the computer.
So, as you may have recalled from the previous experiment, we used the hanging mass, the glides mass, and the force of gravity to calculate an acceleration. And for this experiment, we are actually trying to either change the glides mass or the hanging mass and see how that affects our acceleration. And when we affect our acceleration, that should hopefully give us a percent difference and then a percent error, at least both 2 different values. So as we can see here, we have a table, right? And in case you may have forgotten how we calculated our previous theoretical acceleration, we say that acceleration is equal to the mass being pulled down, right? Or the mass that's actually on the string. And then we multiply that by gravity. And then we divide that by, now again, the mass of the what's being applied to the string plus the mass of the cart itself, right? Or our little boat. And when we do that, we can just, again, replug in our old values. This is just to show this was our 10 grams, and then we're multiplying it by 9.8, and specifically negative 9.8. If you may recall that when gravity is going, or when it's being pulled towards the sensor, then you will have a negative gravity. And if it's being pulled away from the sensor, then you should have a positive one. So in this case, we have it so that it's coming towards the sensor, so we will use a negative gravity right there. And then once again, so this is the weight that's being applied to the string. We'll rewrite it, and then the weight of the boat itself, 95 grams. When we do these intermittent calculations, we should get that our theoretical acceleration is equal to negative 0.93 meters per second squared. And so this is our old theoretical, right? So we know that our hanging mass is 10 grams. We know that our glide mass is 95 grams. And then our theoretical acceleration is negative 0.93, right? And so we're now asked, how can we find the new acceleration given that we've changed either the hanging mass or the glide mass? So we just finished refinding our old theoretical acceleration, and so now that we are going to change either the hanging mass or the glide mass, I'll actually give you a hint, our glide mass is going to stay the same. So we're going to keep this 95 grams, but what's going to happen is that we're going to use the exact same theoretical setup for the acceleration, and instead change this to now 12 grams for our actual hanging mass. We had previously used 15 grams, but when we calculated the percent difference between the original old acceleration and the new theoretical acceleration, the percent difference was, I believe, greater than 33%. So we decided to just increase the mass slightly and only go up by 2. And once again, we're just going to use the exact same formula that we used last time, where the, I'll say this now, A prime value, right, because it's a different acceleration, or the new acceleration, has to still be equal to the mass being applied to the string itself times gravity, and again this gravity will be negative, and then we'll divide that once again by the mass of the string plus the mass of the cart or the little wayboat. And as soon as we plug in these values, right, we should get our new theoretical acceleration. And that new theoretical acceleration should be our 12 grams times our negative 9.8. We'll divide this all by 12 grams again, plus the 95 grams. And so that should give us an A prime theoretical value of, let's see, when I plug and chug this whole mess into the calculator, we should get 117.6 over 107, and then when we do that, it's going to be negative 1.09, and again, this will be meters per second squared. And so now this is our changed acceleration. So now that we've derived both our old theoretical acceleration and our new theoretical acceleration, we can use a formula to find the percent difference between the two. And so again, our old theoretical acceleration was negative 0.93, and our new theoretical acceleration is negative 1.09, both of these being meters per second squared. When we're trying to find this percent difference, we can use the formula percent difference is equal to our reference value minus our tested value, all divided by our reference value once more. And so you may be asking, well, what's the reference value? What's the tested value? When we say these values, the reference value is referring to the old acceleration, and then the tested value is referring to the new acceleration, right? So once again, this is just going to be kind of one of those plug and chugs. And so let's go ahead and plug everything in. If we use our reference value of 0.93, and then we subtract out, right, 1.09, we can actually get, and then divide by the 93. This will give us 0.17. But we still want it as a percentage, so we will multiply by 100. And so that gives us roughly a 17% error difference.
So we're going to be using our software as well.
Yeah. So you're going to just do
And then as well as make sure this the universal interface is connected. And now we're gonna add our graph. And make sure we're on the velocity graph. So when we start the ladder, we're gonna start recording.
After getting our new graph from the added weight, we can go ahead and choose our points so we can calculate the new acceleration for this. And this is like this one as our final point, this one as our beginning point, and we'll use both of these to find the acceleration of the new graph.
So now that we've calculated the theoretical acceleration, and that theoretical acceleration, remember being negative 1.09, we can calculate our experimental acceleration, and we calculated this by using the velocity versus time graph. There we picked 2 points. We picked a v1, a t1, a v2, and finally a t2. And those points ended up being, let's see, 0.14, and then we chose 4.75 for our second velocity. After we chose our second velocity, oh, I'm sorry, I'm placing all the wrong values here. Actually, negative 0.15. Our first time was 4.75 seconds, and our second time was 5.2. And this is seconds, and then obviously you know that this is meters per second squared. All right, so using what we know there, again, we can calculate the experimental acceleration, right? Acceleration prime experimental. And this is going to be equal to our v2 minus v1, all divided by our t2 minus t1. When we plug and chug these values, right, we should get negative 0.15 minus 0.14. And then we're going to divide that all by 5.2 minus 4.75. When we do the intermittent calculations, we should get negative 0.29 divided by 0.45. And finally, that roughly gives us a value of negative 0.64 meters per second squared. So this is our experimental, right? Negative 0.64 meters per second squared. So when it comes to finding the percent error, it's a relatively simple process where we can find the percent error being the theoretical value minus the actual value, all divided by our theoretical once more. When we just plug in our numbers, we should get that our theoretical is obviously negative 1.04, and then we're going to subtract out the 0.64, and then divide this all by negative 1.04 once more. And then if we do these calculations really quick, this gives us roughly 5/13, or a 0.384, and more specifically, a 38.4% error. I'm not letting you write it, but you get our gist. So finally, for the last bit of calculations, we're asked to find the percent difference between the old experimental acceleration and our new experimental acceleration. As you may recall, our old experimental acceleration is negative 0.46, whereas our new experimental acceleration was negative 0.64. Using the percent difference formula, we can go ahead and just find out what's going on, right? If we use our old experiment as our reference value, we do negative 0.46 minus negative 0.64, divide that all by negative 0.46, and then let's just quickly put this into the calculator. And that should give us roughly a 39% difference. Thank you very much. So just to answer a few of the questions that are provided, we pretty much all collectively agree as a group that this is the answer to those questions. So should your old and new percent errors be similar? Why and why not? They should be relatively within the range of one another, just because, again, we are only changing one value, and it is happening to be the 2-gram increase. So when we compare our our percent errors, are they similar? If we have to compare the percent errors, well, specifically when we can did the percent errors, they're relatively within the range of one another. Does our percent error have to be big or small? Does it matter? Yes, it does matter. It matters because we want our percent error to be as small as possible. As you can maybe recall, one of our percent error was 38.4%. That's relatively high, but at the end of the day, these are just the values that we were getting from the experimental and theoreticals. So do you guys agree? Yes, we do. Did we need to rerun both experiments, or experiments in general? We did need to rerun the handful of experiments. Like I said earlier, when we had originally applied the 15-gram weight, our percent error was actually going to be much greater than what we intended. So we had to double down a little bit and kind of go a little bit lower. Was either of our experiments conducting with higher accuracy? I don't think either of them was conducting with either higher and or lower accuracy. I think the motion sensor itself sometimes can be a little bit inaccurate, so it's a little bit hard to place it. And then what could be affecting the accuracy in these two experiments? Well, there's a number of variables that play into this. There's the kinetic friction, the motion sensor itself, the weight boat, there's just a handful of things that could be going on. Thank you.